so start streaming. I think all of our streams are going to start. Okay, we're live. They're all going to start out with trying to figure out whether or not it's actually going on. All right. Welcome to UAB Data Science Club session number 3. Today we're going to go through 3 separate notebooks, but all are machine learning related. The first one's going to deal with model validation, second, underfitting and overfitting, and then the last one will be changing our model selection to use random forests. Again, we're going to use the Kaggle Learn platform. They got a lot of nice information up there for folks that are wanting to do data science stuff. So if we come up here, if you want to find it on your own, you can come on here and go kaggle.com/learn, and it will be right here. And then we're going to scroll down. We'll go to Intro to Machine Learning. And then if you go to the session number 2 video that we did last week, you'll there see that we went through basic data exploration and the first machine learning model. And so today we're going to go through this other set. We're going to go through 7, 9, and 11. So let's get going.
Yeah, and if you go through our second video, your first machine learning model video, it would be a good continuation for you because that entire example is in a continuation, and we'll be talking about model validation based on what we did in our second video. So
yep. So at the beginning of this notebook, it's got kind of a recap of the code that we went through last time. And so up here, you'll see we're importing pandas, which is a data manipulation library in Python. We're also importing the decision tree regressor. So that's a basic machine learning model using decision trees. And then the rest of this is, let's see. So we've got the path to the data that we're interested in modeling. And then we're going to read in the CSV file, split it up so that sale price is going to be our Y, or our...
the field that we're trying to predict on.
Yeah, the field of interest. And then we're going to subset the data based on these particular columns: lot area, year built, square footage, whether or not it's got a full bath, bedrooms above ground, and total rooms above ground. And we're going to subset that into X, or our trading features.
And these are the fields that we feel are going to impact sale price for a house, and these fields would be useful for making a prediction of what the sale price of a house should be.
Yeah, and this is where some of the art of data science comes in, is that trying to figure out what features, or the feature engineering that you need to do to really extract the best model. So we're going to specify the model here. This is just calling the constructor, which then I'll put it in this Iowa model variable, and then we'll fit the model. It's really complicated. We just do Iowa model.fit, and we put our data in, and sklearn takes care of actually doing the model training for us, which is really nice. And then from there we can do predictions and then compare that to the actual values for those particular homes. So if I run that, then you'll see that our first predictions were these, and the second predictions were these. And this was where we left off last time, just noticing that 208,500, 208,500, 181,500, 181,500. The machine learning model appears to have done an extraordinarily good job of predicting our values, which is always fishy when you're designing any kind of model, because we don't expect it to be 100%. So we're going to come down. The first step in this exercise, now that we've reinstantiated our model, is to re-split up our data. So one of the things that happens is if you don't split up your data, then the machine learning model, depending on how many parameters it has, can just kind of memorize your training sample, for lack of a better word.
Yeah, and this is a very important concept in machine learning. Your training data should not be the same as your validation data. Those two data sets have to be separate. So you train on one particular set of data, on one particular data set, and then you validate your machine learning model, how well it has done and how well it would do on another set. That would be a validation data set. So that's what we are going to be trying to do over here. We are going to try to split up our entire data set into these two different, actually three different values, right?
Yes. Yeah, so we have train.
Train and test. Yeah,
Yeah,
so
it's
two.
just train and test, yeah. So in some cases, when you have more complicated models, you may set it up as training, testing, and validation. But for the purposes of this model today, we're just going to split it up into train and test. Now, the first thing we got to do is figure out which function we should be bringing in. They give us a really nice clue here by saying that we want to import the train test split function. So we know that we need to put that over here. And then over here, if we Google where that comes from, let's see, so import train test split. Then here's what we know we need to bring in. So we need to bring in sklearn.model selection. And we'll go back over here. sklearn.model
underscore selection.
There you go. All right. If I run that, it'll say, okay, well, you forgot to actually use the function. So let's do that. So let's train test split. And here we got to do X, Y, and so you'll notice up here it says give it the argument random state 1. In practice, it doesn't matter what your random state is, but since this code has a little checker here, it needs the seed for the random state to be 1 so that it will generate the same samples every time from this, so that it knows that you actually did what you should.
And we get the value for X and Y from our previous section where we actually split up the data, where we so Y again is the field on which we are predicting, and X is the subsection of the fields which should impact the value of our Y variable.
Yeah. And so once this function will spit out 2 different X data sets and 2 different Y data sets. We'll have training X, validation X, and training Y, validation Y. So now we'll scroll down. All right, so now we're going to specify the model. Let's see, so we were using the decision tree model. So I think we can just do that. And then now we're going to fit the model. So we should just be able to do that. But now instead of specifying X, Y like this, we can actually specify train X and train Y. Oh. and I need to put my random state
They ask it again.
equals to 1, yeah. And again, the particular random state doesn't matter except for this particular function, so that the machine learning model or the checker code knows that the values are the same that it's looking for. All right, so now we've done that, and again we see the output that the validation and the prediction and the actual training sample turned out to be the same. So now we're going to have the model try to predict values from a data set that it hasn't seen before. So we'll do Iowa model dot predict. Okay. All right. And here we'll put validation X, right?
Yes. So now it's going to use the same model that it had just created, but now it's going to try to predict the y value for validation underscore x variable.
Yeah. And the important part here is just to remember the model hasn't seen the validation X data set. And so that's where it'll get interesting. So now what we're going to do is see, okay, so my model did really well on the data that it's seen, but if we print out the predictions from data that it hasn't seen before, then how well is it going to do? And let's see. All right, so here, validation predictions, that's the predicted values from the model based on validation underscore X. And then we're going to compare that to what those numbers should actually be. And so we'll do shift return. Oh, what did I do wrong?
Oh, just square brackets.
Oh, square brackets. So there's a few different ways that you can get the top values for an array in Python, and this is just one of them. If you go back through the Kaggle Learn Python section, it'll talk about these specifically. But this basically just says, I want is this the first 5 elements in the
first 5 values?
Yeah, so this is the first 5 values in the array. Similar to Panda's data frame of I want the first 5 values using this head function. Now you'll notice here that our data follows the same general trend, but we're off by quite a lot. So our first predicted value is 186K, and the one here was 231K. And then you'll see, our values decrease with the other values, with the true values, but we still don't come close. I mean, even with this one, 84,000 versus 92,000. So this shows us that just because we did really nicely on the training data doesn't mean we have a quote-unquote good model we could use for generalizable stuff. And so this next step is going to talk about calculating the validation error. So we have a total metric across the whole group. All right, so they've already specified the function that we should use. It's this mean absolute error. So we'll put that in. And then what does it specify here? The predictions and the actual values?
Yeah, the predictions and... So what it's basically doing is it's trying to find the difference between value predictions and value y, the absolute difference, and then just calculating a mean over them.
Yeah.
And that's just going to tell you if that model is usable or not. So for example, if finally the mean absolute error is only $1,000, that means that it has done relatively well. And it could be usable in the future, but if the mean absolute error is pretty high, that just means that it should not be usable. And it depends upon what is your use case, what is your business use case in this case. Are you okay with, like in this case, it's about $30,000. That's the mean absolute error, right?
Yeah.
So do you really think that 30,000 off from the original price, is it okay or not? And
Yeah. And I don't know what the exact Python syntax is, but essentially, like Ravi said, this is roughly what or basically what that mean absolute error function is doing. And you could type something like this in and see. You might have to import another library for absolute value. I can't remember. But basically, here we're subtracting the values from the predictions and then dividing by the total length. I think we also have to put a sum here. So here we're getting the mean or the average of the absolute value of the error between those two predictions, or the predictions and the true values. And as Ravi said, that we got 30,000 is our average error. And I don't know about you, I just bought a house. I'd be pretty mad if the value I paid was 30,000 off of what the value should have been, or alternatively, if I was selling a house and I had that 30,000 off. So we need to do something for our model to be a little bit better. So next, we're going to talk about underfitting and overfitting. All right. So that example of using the decision tree is a good example of overfitting. So it learned really well the training examples, but it didn't generalize well to other data at all. So again, this one, all right, so this kind of recaps the code that we have from the past two Jupyter notebooks. So we'll read in all of our libraries, we'll split up our data, and then we're going to fit our model and calculate the mean absolute error. And so you see that validation mean absolute error was, again, 30,000. So that's what we expected. All right. So let's see. So they said we could write a mean absolute error function ourselves, but they'll supply it. All right. So we don't have to do anything here. This is the mean absolute error function, or how to get it for a set of data.
And you'll notice that we have a new variable over here, maximum leaf nodes.
Yeah.
And so maximum leaf nodes is so both underfitting and overfitting are bad for your model. Overfitting just means that your model has trained a lot on your data set, or on your training data set, and that means if you give it any other data, it might not be that useful. Underfitting it is basically that it hasn't fitted your training data set very well. That doesn't mean that it's going to do well on validation data set. It might do bad on both.
Yeah.
And so the decision tree regressor that we are using, maximum leaf nodes, is basically going to tell how low should it go into the node. So decision tree is basically like decision tree can have multiple layers, right? So maximum leaf nodes defines how many are what's the limit at which you want to be inside your tree.
Yeah, so the leaf nodes helps define how many parameters we're using to fit the model. And the fewer the parameters that you have for a model, the more likely you are to underfit, and the more parameters you have, the more potential there is to overfit your data. If you have done any polynomial fitting of any curves, you've seen, taking just a straight line like a y equals mx plus b and trying to fit it to a scatter plot may not tell you anything. So that would be underfitting. But if you use a high order polynomial like x to the 8th, you can fit almost any data stream once. Because then it's just not going to work in the general case. And so that's the other kind of concept to go with underfitting and overfitting. So the code here that we got to write is to loop through the number of leaf nodes and then retrain our machine learning model for each one of those cases to determine what the appropriate decision tree size is for this particular data. So let's see. So we do something like for leaf in candidate max leaf nodes, something like that.
Yeah.
All right, and don't forget your colon at the end of your for loop. We'll do get may. All right, so we'll put leaf here, and I think we just keep our train underscore x. And so here what we're doing is following the same, oh, see, and I was about to mess it up. So when you're feeding data in here, you're going to want to follow the same structure here. So this is just the definition of the function. And here we're actually putting in our data. So if I put train y in here, it would try to read that in as validation x inside the function. So we're going to put our validation underscore x there, train y, and val y. And then what we'll do is, let's see, may equals that. All right. And then let's see, so we want to figure out what the best leaf node size is. So we'll do something like all right, so first let's just print that out and see what we get. Okay. So we would kind of expect that our code should spit out whatever the smallest error is here. You can see that it starts out high, the error does, at 5, and then it goes down, and then it starts coming back up. So what we need to do is write a little bit of information in here that's going to appropriately select what the best tree size is. So I'm going to just arbitrarily set this to 100,000, and then I'm going to put an if statement in here. If temp may
Is less than
uber may, then best tree size equals leaf. And if I run this, it should just work. I'm going to comment on that. All right. Oh, I have to actually update the Uberme value.
Yeah.
So what happened here is I didn't specify any updating for Uberme, and so it just came back with that same one.
And we need to print the...
Oh, and let's print out the best tree size. There we go.
Yeah, so if you see the 100 one, that's like the fourth value, that's the lowest, 27,282. And
there we go. And then, yeah, so we'll put here. Yeah, so like Ravi mentioned, so 100 was our middle value here, and it was 27,000. So we didn't get a whole lot better than our other situation, but we'll keep on going and see what else we can find. All right, so now we know the best tree size, and we can make it even more accurate by using all of the data and keeping that tree size. So that's just not holding back any of the validation data now that we've decided what our model is going to look like. All right, we can give that a try. So here I think we just put in X and Y, and then we can uncomment this and put in, oh, actually no,
yeah,
that's wrong.
Yeah,
That's random state.
Random state is 1, and we'll also specify our maximum leaf nodes over here.
Oh, I forgot to do that. All right, how do we do that?
So it's just max underscore leaf underscore nodes.
Nodes. And then, so since we're in a notebook, we should be able to just pull it from
Best tree size.
Yeah, so we can just put best tree size, but we know the best tree size is 100. All right, and then here we can put X and Y.
Yeah, and like they mentioned in their notebook as well, now that you have made those decisions, you should be able to put in your entire data here without having to split it between train and test.
Yeah. Again, it might do some overfitting, but we know at least for this particular data set, for this particular model, this is as good as it gets. So that's about as far as this one goes, but there's one more model in this group that I think deals with this data even better, and so that's where we're going to go next. So that's this random forest. So if you're back here, it's exercise 11. All right, so yet again we're importing our libraries, importing our data, doing a testing training split, and then fitting a decision tree regressor machine learning model, calculating the validation error, and then altering the model to use the appropriate hyperparameters, which is the code language for the parameters of the machine learning model, and then checking that error. And we should see that the error goes down from 30,000 to 27,000, and yeah, that's what happens here. All right, so now, of course, before actually running something, they have to tell us that this isn't easy, but we're going to make it easy. So now we're going to basically do the same thing that we did with decision trees, but Scikit-learn has a whole lot of machine learning models that you can try. And so if your model that you're running isn't working, one thing that you can easily do is to just go try another model and just see how well it works. So we're going to pop this random forest regressor in here.
And they mention again random state 1. Again, it's just for their check function.
Yeah, you can have that be whatever you want it to be. All right, so again, we're going to use our validation or our training and testing, our training sets. There we go. Train underscore X and train underscore Y. And then calculate the mean absolute error of your random forest model on the validation data. All right, so this would be, okay, so we could do mean absolute error. And inside of here, we can put, we're going to do random forest model dot predict. Right, and then here we'll put validation.
Validation underscore X.
Okay. And then as our second parameter, we're going to put our validation underscore Y. And then we'll check that. All right. So just real quickly, what happened here is we did a few things in one line. So you can pull this out if you want and do your random forest model prediction and store that in a separate variable and then feed it in here, or Python lets you do things like this where you're kind of nesting functions inside of another function. And so what this is going to do is before it runs the mean absolute error code, it's going to run the stuff on the inside first. So it's going to run this predict, and then it's going to get those output values and feed that as the input parameter to this mean absolute error, which then it'll calculate it here. So you see here our validation mean absolute error for the random forest was 22,000. So so that's quite a bit better. Still, that seems like a little much, but maybe that's just the nature of trying to estimate housing prices.
And plus there are other models that you can try. In the next class, I believe we would be talking about XGBoost, which is supposed to be a very good model for tabular data. But yeah, in this section, I mean, if you are interested, you can try out other machine learning models that you might have heard about. There is k-means as well, which you should be able to find in Scikit.
Mm-hmm. Yep. So we could come here and look at what models are available. Let's see. Let's look at decision tree regressor. All right, so we could go back up one and see, okay, so there's decision tree regressor, there's extra tree regressor. So this is an extremely randomized tree regressor. We can give that a try real quick if we want. I think that would be from sklearn.tree import tree regressor, and then we can just all right, and so you can see the random forest did a lot better than the extra tree because we're back up to 30,000 there. But you can see how easy it is to switch out machine learning models using this scikit-learn format.
Yeah, and you can go into Scikit documentation and try to find some more machine learning models that you want to try on this data set and see how much lower you can get it from this 22,762 number.
Yep. So the other thing that you'll notice, and this is for extra ambitious folks, is this ensemble. So scikit-learn will even let you ensemble multiple models together. So you could take a few different decision trees and then use something like the random forest regressor to ensemble the models together to get an even better prediction, because maybe one model doesn't do well with a certain type of data. The other thing that I would personally look at doing is changing these features of interest, because there may be something else inside of this training data that explains the housing prices better.
Yeah, can we take a look at the columns that are available here?
Yeah, we certainly can. Let's see. Let's put some code here. So what's our, that's in home data. Is that a summary? Is that?
Oh, the columns should give you something, right?
Oh, okay. Yeah. So, like, one thing that I've heard a lot about housing prices is location, 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 and like there's nothing about zip code in here, but perhaps zoning would have something to do with the location.
There is garage adds price and
Oh, yeah.
affects price as well.
Yep.
There are a lot of things that you can actually add to your data set and see how you can actually get it lower than that 22,000 number. Keep in mind, the lower that number gets, better your model is at predicting house prices. But if it goes to 0, there is definitely something wrong.
Yeah.
Something has gone wrong somewhere.
Yep, for sure. So like we could do something like it would be pretty easy to put. Let's see. Neighborhood. I don't know if neighborhood is the right type of data. It might crash on us. So this is an instance in which you might have to do some cleaning. Yeah, apparently that makes it really.
I think it might be also just a check thing.
It's
something
categorical. It's categorical. So you would need to do one hot encoding. So we'll have to do that another day. But you get the idea that you can kind of plug and play and do lots of different stuff. So stay tuned later this week. We'll have, or early next week, we should have the next notebook of the week up. And let us know if you have anything that you want us to cover or if you have any questions.
Yeah, you can post them down in the comment section.
Yep. All right.